Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 4 for January 2024. Let's begin with the first question. Question 1. The equation for a reaction is shown. Some collisions between reactant molecules do not lead to formation of products. What is the best explanation for this? Among the answers given here, the collisions do not have sufficient energy. Of course, we know for reactions to occur, collisions should occur with a sufficient energy as well as the right orientation, but since orientation is not included here, the correct answer should be B. In part B, what are the units of the equilibrium constant Kp for this reaction? Since we have three gaseous components, Kp is going to be the partial pressure of D power 4 divided by the partial pressure of B power 2 and the partial pressure of A power 1. So this is going to be atmosphere power 4 divided by atmosphere cubed, giving us atmospheres, and A is going to be the answer. In question 2, nitrogen pentoxide decomposes in a first order reaction. At 45 degrees Celsius, the half-life for this reaction is 1400 seconds. In an experiment, the initial concentration of nitrogen pentoxide is 1 mole per decimeter cubed. What is the concentration in mole per decimeter cubed of nitrogen 5 oxide after 4200 seconds? So after 4200 seconds, let's see how many half-lives. We're going to do that, divide by that. These are going to be 3 half-lives. So that means if we began with 1, there is going to be a decomposition, or the first decomposition to 0.5, and then 0.25, and then 0.125, and so the answer is going to be a D. In question 3, ammonia is produced by the reaction of nitrogen with hydrogen in the presence of an ion catalyst. Which of the following statements about the catalyst is not correct? It lowers the activation energy. This is correct. That is correct. Reduces the energy cost. That's correct. So alters the enthalpy change of reaction. No, that's wrong. The enthalpy change is not affected by the catalyst. In part B, which conditions favor the highest percentage of ammonia in an equilibrium mixture from identical amounts of nitrogen and hydrogen? Because they said higher percentage of ammonia, and again from that reaction, it means we want to favor the product side, so the temperature has to be lower since the forward reaction is exothermic, and since the product side has fewer gaseous molecules, it means the pressure has to be increased. So higher pressure and lower temperature, and therefore B is going to be my answer. We can see 400 Kelvin is going to be lower than 400 degrees Celsius, and also a pressure of 200 atmospheres is greater than 200 kilopascals, so the answer is going to be B. In question 4, the equations for 3 reactions involving hydrogen are shown. They say what is the order of increasing standard entropy change of the system for these reactions? So to look at the increasing standard entropy change, it means which one is forming more gaseous components. Here we have a solid at the reactant side and we're forming gas, so this is going to be the highest. In this case, we're forming a liquid from gas, that is going to be the lowest, and this is going to be the intermediate. So it's going to be, in increasing order, it's going to be K, and then we go to J, and then L, so the answer should be C. In question 5, methane reacts with steam to produce carbon dioxide and hydrogen, as we can see here. They say the standard molar entropies of the reactants and products are given in the table. Which are these ones here? The value for the S system for this reaction in joule per Kelvin per mole is, the S system is going to be the sum of the entropy of the products minus the sum of the entropy of the reactants. So this gives us the entropy of carbon dioxide 214 plus 4 times the entropy of hydrogen, which is 4 times 131, minus the entropy of methane, which is 186, plus 2 times the entropy of water, which is 189, and then I got that minus that, giving me positive 174 joule per Kelvin per mole, and that is going to be the answer. In question 6, what are the signs of entropy changes at 373 Kelvin when water vapor condenses? When water condenses, the entropy of the system is decreasing, but because it's an exothermic reaction, this is going to be positive, so the reaction occurs because this is going to be positive, although there is going to be a decrease in the entropy of the system. So the entropy of the system is going to be negative, but the surrounding is going to be positive. So C is the answer. In question 7, at 50 degrees Celsius, The ionic product of water Kw is 5.5 times 10 power negative 14 moles squared per decimeter power negative 6. At this temperature, water is, as you can see here, we're calculating the pH, so Kw is equal to the concentration of OH times the concentration of H+. If it is 5.5 times 10 power negative 14, this is going to equal to that, so this is equal to the concentration of hydrogen squared. And so the hydrogen ion concentration is going to equal to the square root of 5.5 times 10 power negative 14. And if we do the negative log of that, so the pH is 6.6 and the water is going to be neutral. So the answer should be B. In question 8, equimolar solutions of 4 acids are prepared. Which solution has the lowest pH? They want you to use the electronegativity values from the data booklet. Chlorine is the most electronegative and therefore it's going to cause the greatest dissociation or loss of the hydrogen, making it have the lowest pH or a lower pH, so the answer should be B. In question 9, some equations for acid-base equilibria are shown. What is the conjugate acid of HPO4 2-? I went through all the equations. So for this, that is going to be the conjugate base because in this case, this is the acid, this is the acid, that is the base. So if we are looking for the conjugate acid of this, it means we are looking for the equation where this is going to be a base. And we can see it's in this equation, this is a base, so the conjugate acid is going to be H2PO4-, so that is the answer. In question 10, what is the pH of 0.2 mole per decimeter cube solution of strontium hydroxide? When strontium hydroxide dissociates, it produces 2 moles of hydroxide. So if we know the concentration of strontium hydroxide, the concentration of hydroxide is going to be double that, meaning it's going to be 0.4 mole per decimeter cubed, and so the pH is going to be 14 minus POH, or 14 minus the negative log of 0.4, giving us 13.6, and so the answer is a B. In question 11, carvon is an oil used in aromatherapy. We can see carvon here. They say carvon shows. If we look here, carvon has a chiral center, so it's going to show optical isomerism, and therefore the answer is going to be C. Next, they say which reagent gives a positive result when added to carvon. Carvon contains a carbon-carbon double bond and a ketone group, so 2,4-dinitrophenylhydrazine is going to give a positive test, so the answer should be a D. How many peaks would be expected in a carbon-13 NMR spectrum of carvon? So let's count the number of carbons that are different. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're going to be 10 different carbon-13 NMR peaks, so the answer is going to be A. Next, they say from which reactant could this be made? This is an ester, so we could use an alcohol and a carboxylic acid. The carboxylic acid should be 4 carbons, meaning from butanoic acid, and then the alcohol should be pentan-1-ol, so the answer should be that. In question 13, the reaction between ethanoic acid and lithium tetrahydroaluminate 3 is best described as? This is a reducing agent, so this reaction is going to be reduction. In question 14, which substance is the least soluble in water? Solubility in water depends on the intermolecular forces of attraction formed, and in this case, formation of intermolecular hydrogen bonds. Propan-1-ol is an alcohol, it can form, the carboxylic acid can form, and the sodium propanoate has some degree of solubility. So propanol cannot be able to form a lot of intermolecular hydrogen bonds with water, therefore it's going to have the least solubility. And in question 15, the mass spectrum of compound X shows a large peak at mass to charge 59. This peak is due to the fragmentation of a molecular ion. Which compound is most likely to be X? Because X has a peak at mass to charge 59, these ones here have no peaks at mass to charge 59 except this one here due to that, so the answer is going to be A. In part B, compound Y does not react with acidified aqueous sodium dichromate. The infrared spectrum of Y is shown. If it does not react with acidified aqueous sodium dichromate, then it's not a primary alcohol, it's not a secondary alcohol, and it cannot be an aldehyde. But there is a possibility that it could be a tertiary alcohol. So they say which compound is most likely to be Y. They want you to refer to the data booklet. And when I refer to the data booklet, this peak here stands out in ketones. So because it's not an aldehyde and this is significant for carbonyls, it is going to be propanone, which is the ketone. So the answer is D. So this brings us to the end of section A. Let's continue to section B. In question 16, a group of students investigated the kinetics of a clock reaction. The reaction investigated was that between hydrogen peroxide and iodide ions in the presence of acid. So you see the first reaction is given here. And in this clock reaction, a fixed volume of aqueous sodium thiosulfate and a small amount of starch were added to the reaction mixture. The added thiosulfate ions react with the iodine, which is produced in reaction 1. And then in reaction 2, we see again another equation. This is between thiosulfate and iodine. When all the thiosulfate ions have reacted, the presence of iodine is detected by the formation of a starch-iodine complex. The students recorded the time taken for this complex to form. Then they say state the final color of the mixture containing the starch-iodine complex. Because in the end we have to form the starch-iodine complex, this complex is going to be blue-black, so that should be the answer. And they say under appropriate conditions, the reciprocal of time can be used as an approximate measure of the initial rate of the reaction. Explain why the concentration of sodium thiosulfate must be low compared with the initial concentrations of other reagents. If it's made lower, then it's going to be the limiting reagent so that it can be used up. So I said thiosulfate will be the limiting reagent. It will therefore be used up before other reagents are. This ensures that the rate of reaction is not affected by the concentration of the other reagents. And in part B, for reaction mixtures with different initial concentrations of hydrogen peroxide, hydrogen ions and iodide ions were prepared. Each mixture had the same volume and contained the same amount of sodium thiosulfate and starch. They say use the results in the table to deduce the order of reaction with respect to hydrogen peroxide, hydrogen ions and iodide ions. You should justify the answer by referring to relevant data from the table. I'm going to begin by considering experiment 1 and 2. We can see the concentration of hydrogen peroxide is halved and the rate is also halved. So that means it's going to be first order with respect to hydrogen peroxide. Going to mixture 1 and 3. When the concentration of iodide is doubled, the rate also doubles. So that is going to be first order with respect to iodide ions. And going to reaction 1 and 4, when the concentration of hydrogen is multiplied by 10, it's almost like there is no change in the initial rates. So that is going to be zero order with respect to hydrogen ions. So they say write the overall rate equation for reaction 1 using your answer to be 1. So the overall reaction is going to be rate is equal to K into the concentration of hydrogen peroxide. Remember that order is 1 times the concentration of iodide, whose order is also 1. So order with respect to hydrogen ions is going to be 0, and therefore it will not show up in the rate equation. And next they say all 4 mixtures contain 8.50 times 10 to the power negative 5 mole of sodium thiosulfate. Calculate the amount of iodine that had reacted with the sodium thiosulfate when the color changed in reaction 2. So moles of iodine, they're going to be half the moles of thiosulfate based on the second reaction. If I take you back here, the moles of iodine are half of that because the ratio is 2 to 1, which is going to be half of that, giving us 4.25 times 10 to the power negative 5 mole. And next I say calculate the rate of reaction in mole per decimeter cube per second with respect to hydrogen peroxide using the answer from B3, the stoichiometry of reaction 1, and the data from mixture 1. For mixture 1, we get the time which is 195 seconds. From B3, the moles of iodine are 4.25 times 10 to the power negative 5 moles. And also from reaction 1, the moles of iodine are equal to the moles of hydrogen peroxide, which is going to be that. So I can begin by calculating the loss or change in hydrogen peroxide, which is going to be the concentration of hydrogen peroxide divided by time, which is that divided by 195, and that was the rate or loss of hydrogen peroxide. Second, it's going to be that divided by the volume, because I already have mole per second, so I need to do per decimeter, so divide by the volume, and it gave me 4.36 times 10 power negative 6 mole per decimeter cube per second. And next, calculate the value for the rate constant of reaction 1 using data from mixture 1 and your answers in B2 and B4. Include the units of the rate constant. From B4, rate is given as that, and from B2, the rate equation is rate is equal to K, concentration of hydrogen peroxide times the concentration of iodide. So K is equal to rate divided by H2O2 and that. Substituting that is going to go here in place of the rate, and then the different concentrations, like for hydrogen peroxide here, we're using reaction 1. We have this concentration, that concentration, and then the answer is going to be 9.85 times 10 power negative 3 decimeters cubed per mole per second. In part C, the activation energy for reaction 1 may be found by repeating the experiment at different temperatures. Each student carried out an experiment at a different temperature. One of the students misread the thermometer in their experiment. So these are the results we have here. They say the activation energy for a reaction may be found by plotting a graph of natural log of rate against 1/t, and the gradient of the resulting line of best fit can be used in the Arrhenius equation to determine the value of EA in kilojoules per mole. Determine the value of EA for reaction 1 by plotting the graph using the axis provided. You should take in account the error made by one of the students. So I want to go look at that first before coming back here to do the calculation. This is plotting the values that were given. Of course, on the x-axis we have 1/t in per Kelvin, and then we have the natural log of rate. And the positioning of the points appropriately, and we can see this is the value that was misread. I was able to draw the line of best fit through all the other points. So from the graph, the gradient, which is negative EA over R, I found the gradient using this value here and that value. We can see the coordinates that and that. So my gradient was negative 4.6 minus negative 3.2 divided by the 0.0034 minus 0.0032. And I got that for negative EA over R. So EA is going to be that times R, where R is 8.31, and I got 58170, which is, this is going to be in joules, but converting it to kilojoules, it's going to be positive 58.2 kilojoules per mole if you divide by 1000 and write your answer to 3 significant figures. So the answer here is 58.2 kilojoules per mole. And then they say that students all use thermometers capable of reading to the same precision. Use your graph to deduce the temperature that the student who made the error should have read on their thermometer. This value should correspond to this point, which should correspond to 1/t value 0.003315. T should equal 1 divided by that, giving us 301.6591252, which is basically 302 Kelvin. So this brings us to the end of question 16. Let's continue to question 17. In question 17, the equation is about lattice energies. The table shows energy values used in a Born-Haber cycle for magnesium chloride. So these are shown here. They say complete the Born-Haber cycle for magnesium chloride by adding labels for each of the 4 energy changes and writing formulae in the 2 empty boxes. So the first one, which is enthalpy change of atomization of magnesium, that is A, magnesium solid being converted to magnesium gas, so it should be that. Then B, first ionization energy of magnesium. This is going to be Mg gas becoming Mg plus gas, which is this one here. And then we go to the second ionization energy of magnesium. Again, this is going to be Mg plus converted to Mg2 plus gas, that is C. Then next we go to the enthalpy change of atomization of chlorine. That is chlorine gas, Cl2 being converted into Cl. So this is going to be from here to here, so 2 times D. And then the lattice energy of magnesium chloride, which is going to be E here. Calculate the value for the electron affinity of chlorine in kilojoules per mole using the data in the table and the complete Born-Haber cycle. This one here, twice the electron affinity is going to equal, if I'm moving from this way to this way, so I'm going to reverse everything. So it's going to be negative 2D minus C minus B minus A plus F and then minus E to be able to get that. So substituting the corresponding values from the table, EA is equal to negative 348 kilojoules per mole. Explain why when magnesium reacts with chlorine, MgCl2 is formed rather than MgCl3. To form MgCl3, we will have to carry out more ionization of magnesium, and that requires more endothermic energy that may not be compensated for when magnesium chloride forms. However, to form MgCl2, we just ionize magnesium twice, and the energy is compensated for when magnesium chloride forms, so that reaction is going to be achieved. So I say to form MgCl3, Mg3 plus cation has to be formed, and this requires more endothermic ionization energy. This can be compensated for when MgCl3 forms, but for MgCl2, Mg2 plus has to be formed, and this requires less ionization energy that can be compensated for by lattice energy. Calculate the standard molar enthalpy change of solution of magnesium chloride in kilojoules per mole using the data shown and the value for the lattice energy given in the table. The enthalpy of solution is equal to the negative of lattice energy plus the sum of the hydration energies of the two ions. So this is going to be negative lattice energy plus the summation of hydration enthalpy, which is negative 2526 plus negative 1920 plus twice negative 364, giving us negative 122 kilojoules per mole as the enthalpy of solution. Then in part B, they say lattice energies from the Born-Haber cycle are based on experimental values. Theoretical lattice energy can also be calculated. Experimental and theoretical values for three different crystal lattices are shown. So we have sodium fluoride, magnesium fluoride, and magnesium chloride. So here we can see this is almost identical because there is less polarization, and therefore the difference between the theoretical and the experimental is almost non-existent. It's like sodium fluoride is almost 100% ionic. Now when we compare magnesium chloride, because magnesium is a smaller cation, it's going to cause a lot of polarization or distortion of the electron cloud on chloride more in comparison to fluoride. So the difference between the theoretical and experimental here is going to be greater because magnesium chloride has more covalent nature. So they say discuss the reasons for the differences in these 6 values of lattice energy in terms of the structure and bonding in the 3 substances. So we have sodium fluoride, magnesium fluoride, and MgCl2. These are all giant ionic compounds. The greatest difference between the experimental and theoretical lattice energy is in magnesium chloride, while the least difference is in sodium fluoride. Mg2 plus has a smaller cation or the smallest cation and the greatest charge. So Mg2 plus has the greatest charge density and the greatest polarizing power. And Na plus has a bigger size and a smaller charge compared to Mg2 plus. So Na plus has a low polarizing power, meaning it does not distort the electron cloud as much. Chloride anion is larger than fluoride anion, so the electron cloud of chloride is easily distorted in comparison to that of fluoride. So due to the polarizing power of magnesium, the bond formed in MgCl2 has greater covalent nature than in NaF, and the MgCl2 or the bonding is stronger than theoretically presumed. So the lattice energy released in the bond formation is more exothermic, causing a greater difference between the theoretical and the experimental lattice energy. So this brings us to the end of question 17. Let's continue to question 18. In question 18, methyl 2-hydroxypropanoate is used as an industrial solvent. It may be prepared in 3 steps using ethanol as the starting material. They say name the reagents in step 1 and 2. In step 1, we are converting an aldehyde into a hydroxynitrile. So here we'll need potassium cyanide and HCN. And in step 2, we're converting the hydroxynitrile into a carboxylic acid. This is hydrolysis of nitriles, so we can do that in acidic conditions. That is going to be acid hydrolysis, so we need acid and water. Then they say complete the mechanism for step 1 using curly arrows and relevant lone pairs, charges, and dipoles. Here we begin by positioning the partial charges, and then a lone pair from the carbon in the CN is going to be donated to the partially positive carbon, and that bond is going to break, creating a negative charge on the oxygen as the CN attaches onto that carbon. Then in the next step, the HCN comes in, and the lone pair on oxygen is going to be donated to the hydrogen. As that bond breaks away, create this hydroxynitrile and the CN minus. Explain why the 2-hydroxypropanoic acid produced is not optically active. If I take you back here, around this carbon is going to be planar, so the CN can attack from either side, creating two possible enantiomers that could be equimolar to have no overall optic activity. So I say the molecule is planar around the carbonyl carbon, so the CN can equally attack from above and below. Two enantiomers in equimolar concentrations are formed. One is an L isomer and the other is a D isomer, so a racemic mixture is going to be formed. Then state the type of reaction in step 3. That is esterification, and ester is formed. Then they say a small amount of a polymer compound is formed during step 3. Deduce the structure for the repeat unit of the polymer. Here we have a compound that is both a carboxylic acid and an alcohol. This is a reaction between the carboxylic and alcohol groups, so the repeat unit is going to be that. In part D, the high-resolution proton NMR spectrum of methyl 2-hydroxypropanoate gives 4 peaks. There is J, K, L, and M. Peaks L and M are singlets with the relative intensities of 1 to 3 respectively. Label the displayed formula to show the protons responsible for these 2 peaks. This is going to be a singlet because the neighbor doesn't have any hydrogens. This is also singlet. This one here will be a doublet and this is going to be a quadret, so this is singlet and that is singlet. The next I say complete the table to show the expected number of hydrogen atoms and the expected splitting pattern for peaks J and K. For J at chemical shift about 1.3, this is going to be HCC. So this is going to be the doublet, this one here. There are 3 hydrogens in that environment. And then for the other around 4.1, it's going to be the HCO. This is going to be 1 hydrogen in that environment and it's going to be a quadret because the neighbor or adjacent carbon had 3 hydrogens. So this brings us to the end of section B. Let's continue to section C. So question 19, they say ethyl propanoate smells of pineapples and is used as a flavoring. It may be hydrolyzed using hydrochloric acid as a catalyst to produce propanoic acid and ethanol. So that is the equation. A mixture was prepared using 0.1 mole of ethyl propanoate and 0.2 mole of water containing the catalyst. The mixture was left to reach equilibrium at 25 degrees Celsius. The equimolar mixture contains 0.044 mole of propanoic acid. Calculate the value for Kc for this equilibrium at 25 degrees Celsius and give your answer to an appropriate number of significant figures. So I wrote the equation again and then placed the components from the question. So we have 0.1 initially, and that is going to be 0.2. The products have 0 moles initially. They say at equilibrium we have that of propanoic acid. So this is the acid. And since the equation is 1 mole for each, it means also the alcohol is going to be the same. So since these are formed for the product, it means they're going to be subtracted from the reactant. And again, maintaining the mole ratio. So if this lost that, it means whatever is remaining is going to be that. That minus that gives us that. So the equilibrium moles are going to be that, 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 and that. So Kc is going to be the concentration of that times the concentration of that divided by the concentration of that times the concentration of that. Here we consider water because everything is in liquid state. So substituting the moles, and again here we have to use concentration, but since everything is in the same volume, I can just apply volume and the V can cancel out. So this is the concentration of the acid, concentration of the alcohol, concentration of the ester, and the concentration of water. Cancelling out the V's and multiplying everything, I got 0.222 as my answer, the value for Kc, and there are no units. And then they say the standard enthalpy change for this reaction is close to, but not exactly 0. Explain this statement by considering the type and number of bonds being broken and made. No calculations are required. I displayed out whatever is on the reactant side and the product side, and I realized that each side has 10 carbon hydrogens, 3 carbon-carbons, 1 carbon-oxygen double bond, 1 carbon-oxygen single bond, and 2 oxygen-hydrogen bonds. That is why the enthalpy change of reaction is almost close to 0. So I say they all have the same number and types of bonds broken. The small difference in the enthalpy change of reaction is because the bonds are in different environments. Next, they say deduce the effect of increasing the temperature on the total entropy change of this reaction and on the value of the equilibrium constant Kc. Assume that the S system does not change with temperature. We know that ds total is equal to ds system plus ds surroundings, which is the same as ds system minus delta H over T, but they say ds system does not change. If it does not change, yet temperature is increasing, the magnitude of the ds surrounding is going to be decreased. The change in ds total is not going to be that big. Also, ds total is equal to R, natural log of Kc, so since ds total will not significantly change when temperature increases, Kc will not significantly change as well. Propanoic acid is a weak acid. State the difference between a weak acid and a strong acid such as hydrochloric acid. A strong acid like hydrochloric acid goes to completion when it dissociates, while a weak acid dissociates to a smaller extent. Calculate the pH of 0.5 mole per decimeter cubed hydrochloric acid at 25 degrees Celsius. Because HCl dissociates to give hydrogen ions and chloride, if 0.5 mole per decimeter cubed of HCl is present, it gives 0.5 mole per decimeter cubed of hydrogen ions. So the pH, which is negative log of hydrogen ion concentration, is going to equal to negative log of 0.5, giving us 0.3. Calculate the pH of 0.5 mole per decimeter cubed propanoic acid at 25 degrees Celsius. They've given us the Ka at the same temperature. Because this is propanoic acid, it can dissociate, as we can see in this equation. And at equilibrium, the concentration of that and that are the same. So Ka is equal to the concentration of H plus squared divided by the concentration of that. Also, because this is a weak acid, the dissociation is not that big, so the equilibrium concentration and the initial concentration of the acid are the same. So, substituting Ka and the concentration, the H plus concentration is equal to the square root of 1.3 times 10 power negative 5 times 0.5, which gave me that. So pH is the negative log of that, giving me 2.5935, which is 2.6 as the pH. And next they say the number of moles of propanoic acid in a solution may be determined by titration with aqueous sodium hydroxide. Calculate the pH at the point in the titration where half the acid has been neutralized. You must show you're working. At half neutralization, these concentrations are going to be the same, and the pH is equal to pKa, which is negative log of Ka. So substituting the Ka value, pH is going to be the negative log of Ka, which is 4.8860566648, rounding off to 4.89 into 3 significant figures. And next they say, sketch the titration curve showing the change in pH when 50 centimeters cubed or 0.5 mole per decimeter cubed sodium hydroxide is added to 25 centimeters cubed of propanoic acid of the same concentration using your answers to B3 and C1. So in B3, we were talking about the acid before the sodium hydroxide was added, so that is the pH at the beginning, which is about 2.6. Since neutralization required 25 centimeters cubed of sodium hydroxide, at half neutralization, 12.5 centimeters cubed will be used, and the pH at that point is 4.89, which is about there. So the key points in my curve were that pH and this pH, and then at 25 centimeters cubed, I had to show a vertical region. And since sodium hydroxide is a strong base, the curve had to curve in within the region for the stronger base. So that is the shape of my curve. And next I say, suggest a suitable indicator for this titration. Justify your choice by referring to your titration curve in C2. Use the data booklet. Using the data booklet, the pH should have a range within this region, and phenolphthalein indicator was my choice. So I say it because it's pKin, or you could say its range lies within the vertical part or vertical portion of the titration curve. So this brings us to the end of question 19, as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.